Okay, we're going to talk about telescopes. Let's start with the basic design of telescopes. And what I'm drawing here is known as a refracting telescope. It's one that uses two lenses. The first lens, or the one that the light initially comes through, is known as the objective. Sometimes also referred to as the primary. And then this other one, that's what you look through. That's known as the eyepiece. Now, obviously we're using a telescope to look at something. Generally it's something far away, but I'm just going to pretend that we're looking at some person that is some distance away. And the light from that person is going to pass through the objective, and an image, a real image, is going to be created by the objective. And that image is what the eyepiece is looking at. The eyepiece is looking at this real image created by the objective. And then, of course, you have the eye over here looking through the eyepiece to see the final image. The one, of course, this is the image created by the eyepiece. Now, let's go through the general setup here, how the math is going to work, I guess is what I'm really saying. So we'll start with our optic formula. 1 over f equals 1 over do plus 1 over di. Now, generally, when you're using a telescope, the point is to look at something far away. You're not looking at something up close. That's not the point. You're looking at something that's far away. And so the object distance is going to be quite large. And more importantly, it's going to be quite large in comparison to the image distance and probably the focal length as well. And actually it will be. It'll be much larger than both of these. So if the object distance is much greater than the focal length, and consequently, and as a consequence, it's going to be bigger than di, the image distance, automatically, and you'll see why. But if that's the case, then what happens? That means that 1 over do is going to be negligible. And so we can set this equal to 0. It, of course, might not be 0 exactly. We're just saying that it's pretty darn close to 0, enough to be negligible. And as a result, since this is 0, what does that mean? That means that in our formula, we're going to have just 1 over f is going to be approximately equal to 1 over di, 1 over the image distance. And that means the focal length is approximately equal to the image distance. So in that case, that means up here, this is the image distance. But since the person is very far away, our object distance is quite large, this approximation holds, and that makes this just the focal length of the objective, which we represent with an f sub 0. So that's what's going on there for the objective. Now, let me go over what's happening with the eyepiece. And I'm going to have to make a little space here, so let me erase what I just wrote. It's going to be very similar when we're dealing with the eyepiece, but instead of the object distance disappearing, it's going to be the image distance that ends up going away. And let me show how. It has to do with how our eyes work. When you're looking through the eyepiece, you want your eye to be in the most relaxed state. And the reason why is because when people were first making telescopes, you know, they would be looking through them, astronomers would be looking through them for a long time. You don't want to wear your eye out. You want it to be nice and relaxed. And really this goes for anybody. It's just easier, even if you're just looking through it for a short time. You want it to be relaxed. And it turns out that when your eye is relaxed, that's when it's best for looking at objects that are extremely far away. You might say an infinite distance away. And so we want the light, to get our eye in that state, we want the light coming from this image to come out and be parallel. We want that light to be parallel. That'll put our eye in the relaxed state, because it'll have to be in the relaxed state to bring these light rays into focus. This corresponds to an image that is an infinite distance away. So in this case, the image distance is equal to infinity. And since it's equal to infinity, that means 1 over the image distance is 0. And because that's 0, that's going to mean that 1 over the focal length is equal to 1 over the object distance, which of course means that the focal length, in this case, equals the object distance. This is the object distance from here to here. That's the object distance for the eyepiece, which is going to correspond to the focal length of the eyepiece. That's going to be the focal length of the eyepiece. And what you can see is that this distance, the focal length of the objective plus the focal length of the eyepiece, that's going to be the length of the telescope. Now, strictly speaking, it's the minimum length of the telescope. You would only achieve this when you were looking at objects that were sufficiently far away. As objects get closer, the objective would move outward, or the eyepiece would move outwards, one of them, but the distance between them would increase slightly. But again, what are we using telescopes to look at? We're looking at stars, we're looking at planets. These are all things that are very far away, and so to any appreciable measure, this is going to be the length of the telescope. Now, this is the length, I should say, of a refracting telescope. There's another type of telescope, it's called the reflecting telescope. Let me just briefly show you how that works. The reflecting telescope works in the following way. You have what's called the primary mirror, and the light's going to come in. The light comes in like so, hits the primary mirror, and it reflects this way. And you could have your eyepiece over here, but generally what we do is we put a secondary mirror. It's just a flat mirror usually, and that's going to bounce the light back toward the primary mirror. And so what they do is they put a hole in the primary mirror so that light can pass through. And then you put, now I've exaggerated how far back, but you put the eyepiece back here. So this would be the eyepiece, this would be the what's called the primary mirror, could also be called the objective mirror, and this is the secondary mirror. And you can see, even though my diagram isn't the best, that this shrinks how long the reflecting telescope is. So this length only corresponds to the length of the refracting telescope, but what it always corresponds to is the distance that the light actually has to travel after hitting the objective or the primary. So it has to travel a certain distance between the objective and the eyepiece in order for you to get a nice focused image using the relaxed eye. Now, that's the reflecting telescope. I want to show it to you, but we're not actually doing any problems with that. We're just focusing on the basics. We're just focusing on the refracting telescope and how it works. The things that are extremely important for you to remember. Okay. First off, this approximation that if the object distance is much greater than the focal length and consequently the image distance, that means 1 over DO is approximately 0. That's important to remember. Another thing to remember, for the relaxed eye, the image distance equals infinity. That's important to remember. And then, of course, we have our formulas. This is the formula for the length of the telescope. And there's one other formula. I haven't mentioned it. It's for the magnification. I'm not actually going to go through and derive this. There's really nothing to gain. Although if you are interested, I'm happy to show you how it comes about. It's not complicated. Negative FO over FE, that's our magnification formula for the telescope.